All right. I usually start these lectures with a motivation of where do you need this in computer vision, which problem will this algorithm allow you to solve, why should you care? Today, I don't really want to start with that kind of motivation. Rather, I think the central reason to buy this today is because it is such a nice unifying theory. What is it? A formulation of the algebraic path problem, which allows us to bring the shortest path, the widest path, the existence of a path, and actually many other path problems under a single theoretical framework. And as I think I said earlier, there is no grand unifying theory of computer vision, but paths and computing some notion of short path are really pervasive concept in computer vision. And it has this tight connection to dynamic programming, which we need also in the neural network world. Backpropagation is one example of dynamic programming. And as a reminder, we did look at many shortest path problems. We looked at shortest path, we looked at widest path. When we talk about shortest path, we were looking at settings like this one, or seeded segmentation, or importantly, map inference in open chain discrete graphical models, and many other use cases. So these are all places where we need some kind of short path. And today we will bring them all together, under a single theoretical framework. So here is some pseudocode we've seen before, Dijkstra's algorithm. And let's remind ourselves briefly what happened. We have a single source S. The distance of the source to itself is set to 0. The distance to any other node U in our set of vertices V except of S is set to infinity. All of these nodes are put onto a queue.
You forgot to start the sharing the screen, maybe.
Yep, I should do that. Thanks, Alberto. We add these all to a queue and then extract or pop these nodes from the queue one by one. For each node V that we pop, we look into its forward star. So we are looking at all connections to nodes U, which are adjacent to V. So when we have connections from V to U, these are the U's that we consider. And then we update the costs of reaching node U from our source S. And we have different recipes for this update. And we looked so far at this particular update rule here. So we had already some previous cost from the source to node U. After initialization, this cost was infinity. But generally speaking, it's the cost of the cheapest path found so far. And we now have a new alternative path, namely the cost of going up to V plus the cost for going from V to U, so the cost of going along edge E. And now we ask, which of these two is smaller? And well, if the newly found path is smaller, then its cost replaces the old cost. And that gives us the classical shortest path. We also looked at minimax path, or widest bottleneck path. Here we considered the old cost. And for the new cost, we looked at the cost of going to V and the cost of the new edge and which of the two was larger. In other words here, the only thing that matters is the single most expensive edge as we walk along a path. And iterating that in this algorithm gives us the minimax path, which is the basis of the watershed, of the minimum spanning tree, and so on. Today, and actually this algorithm is very general. We could invent many other rules. Today I want to introduce here a new color, the question not about the shortest path or the minimax path, but the question, is there a path at all? Now, this is a special case of the above. Let's create a graph that has edge weights of 0 for edges that exist, and well, the non-existing edges, we could code them in a complete graph by assigning a cost of plus infinity to those edges. And then I could work with these costs, or I could also decide to work with Boolean operators here. I could say that the edges are either absent or present, so false or true, in which case I would initialize the source as being true and the rest as being false. And we then update with the following statement. So along a path, each single edge has to be true. This is what the AND statement does. But if we consider many paths, then just one of them has to be true. That's what the OR statement does. And so this is yet another update rule, which solves yet another class of problems, namely the question, is there a connection at all between my source S and any other given node? So let's look at applications for this. I've mentioned two reasons here why this is needed in computer vision. Oftentimes let's say you're training your network to detect something, and then you threshold, and then you want to collect all these pixels that are within the same island or within the same connected component within the same island above the threshold. And the algorithm just described, it's not the one you would really want to use, as I will explain in a few minutes, but as a problem, it does fall within this general class of algorithms, or it can be solved by this family of algorithms that we've just seen. Or it can be used to solve problems which can be called reachability in networks or percolation. So percolation is the question, let's say we have a solid, we fill in water from the top, as you can see here. And then the question is, well, will there water seep out at the bottom, yes or no? And here we have different probabilities of white versus black pixels, where white is accessible to the water flowing in from above, and black is solid and not permeable. And as we fill in water from above, you see here it does reach the bottom, and these are just random images. Here it does not reach the bottom, and here the water does not even get very far. So this would be percolation. And of course, this is a much studied problem in theoretical physics, where you try and study the probability of percolating as a function of this probability of having black or white nodes. But if you want to know if a concrete realization percolates, well, you can use this kind of algorithm. Or here's a bigger example, just to show what such a percolation front here shown in red can look like. All right, so we have used the same skeleton of an algorithm with just a different update rule in here, and this single kind of algorithm has allowed us to solve the shortest path problem, the minimax path problem, or the existence of a path problem. And this is what I wrote here. A generic single source, I call this generalized shortest distances, because these are various notions of shortest distances. A single source generalized shortest distance algorithm finds the shortest path, the widest path, paths at all, and actually ... a few more. And a nice paper studying this algorithm and its complexity is the one that I cite here by Mori. So this is all great. And now the disclaimer. these problems do have a bit of a different structure after all. So, for example, in this question, is there a path at all? Well, if we happen to have this particular algorithm implemented, this generic single source one, and our problem that we need to work on is small, that we might just as well use it. But if we need to solve this connected components problem often, or if speed matters, then there are more efficient algorithms because the combinatorial nature of the problem is different. And this is the disclaimer I made here. Everything I said is true, but the actual implementation for this question of is there a path, and that's something you've used already or are using in your current exercise, is to use a disjoint set or a union find data structure. Why? We've talked about graph partitioning before, and if I have a few nodes, I'm just considering a 1D example here, then if I want to ask, are any of these two nodes connected or not, I can either answer this question in the world of graph edges, or I can, so in terms of edge labels, or I can answer it in terms of node labels. Now, if we talk about edge labels, let's see, I have 10 nodes here. If I want to answer the question, are any two nodes connected here? If I want to answer it very quickly in terms of edge labels, then I need this complete matrix. Yeah? So I have a 4x4 block here, which is filled with ones, because the 4 nodes to the left are connected. And it's getting a bit small. Then I have 3 isolated nodes. So I have a 1 here, a 1 here, and a 1 there. And another block diagonal with 3 ones. The rest is all filled with 0. So if I have this matrix, then I can just answer in constant time for any two nodes, let's say I and j, if they are connected or not. Now, because this, so let's say I have n nodes here, and because this is an n squared matrix, you see that somehow, if I want to construct this matrix, there is, I will eventually need to fill all the elements in that matrix, or perhaps I find a mechanism to say, at least I would need to fill these block diagonals. And you see that they grow quadratically with the size of the components. So that's not really something which is possible to do in linear time. So it's not really possible to do this in just n steps. However, if we are willing to use node labels, then, if you think about this for 30 seconds, as we scan from left to right, to invent an algorithm that gives us the same label for all connected nodes, within 30 seconds you will come up with an algorithm. The algorithm would do something like this. It would start from the left with an arbitrary node label, which we call 1. And if there is a connection, then it just copies that label. And then if there's no connection, we start with a new node label. If there's no connection, new node label, no connection, new node label, no connection, new node label, and then we have a connection, so we copy the label again. All right, so this time I just have this linear vector of node labels, and if I now want to ask if I and j are in the same component or not, then I look up the label for I look up the label for j, and I ask, are they the same or are they different? And I can construct this in linear time, and I can query this in constant time. So this is an example of solving this particular problem in one dimension more efficiently. Now, the really interesting problems are never one-dimensional. At least we want to work with a planar graph and more generally speaking with any graph. But it turns out that even for arbitrary graphs, there is this super efficient algorithm and data structure, which, if we have time, we will talk about at the end of today's lecture, which is based on this idea of node labels rather than edge labels. All right, so we have seen a unifying algorithm in terms of single source shortest path, and next I want to give you a unification of the all pairs shortest path problem in terms of matrix operations.